I would like to introduce Patrice Brissette, who will be presenting EVPN multi-site architecture, seamless data center interconnect with fault isolation. Patrice is a distinguished engineer at Cisco Systems and traveled from Ottawa, Canada to join us today. This is Patrice's second time presenting at NANOG, and it's a pleasure to have him returning to the NANOG stage to speak with us today. Welcome back, Patrice.
Hi. Hi, everyone. Thank you for being here. Thank you for being so courageous at that time, so to attend the session. I'm glad to see a bit of people. I was kind of afraid if I would have been alone in this room or not, but that's cool. All right, so today we're going to be talking about the interconnects, what I call also sometimes like multi-site technology. It's all about how we connect, expand data centers or IP fabric into like either bigger data center or just how you connect them into the networks, okay? And it's all about how you stretch your control plane, your EVPN, your underlay, without causing like tons of issue in that middle place where everything is gathering together. So the agenda would be 4 major parts. The first thing is just high level of the architecture. What is the spirit? What is the mindset behind this? Then we're going to go through a bunch of concepts so everyone can talk the same language. And then we go through all the flows, packet flows, how the network will work, and obviously the isolation and failure. So you can tell me that yes, it's working. So. All right, the architecture. So conceptually speaking, what we are doing is, you will see it especially in those pictures, is that we have fabrics, and I put here especially IPv6 on the fabric and IPv4, IPv6 on the one. It's just to open your eyes that it doesn't need to be all the same, right? You can do V4 to V6, V6 to V4, who cares? But what is very, very important is on the border gateway, where the DCI functionality is applied, is a full termination of the service there. So therefore, if you do VXLAN within your data center, all the tunnels are getting completely terminated at the border gateways. You do your lookup based on your service. If this is L2, you do MAC lookup. If this is L3, you do IP lookup. And then, based on your routing table, you will decide where you go. So therefore, we will do a full re-encapsulation of the packet, okay, to that new tunnel. So now here, if you look at where I wrote external one, is basically just a transport zone between those two fabrics so they can intercommunicate between them. But there's no like kind of other type of new service there. It's just like, I'm stitching these guys, okay? So that is the high level architecture. But where it starts to be very interesting is when you start playing with the concept. Okay, so forget about everything you know about how we construct your data center, you connect to a WAN, and this is a DCI things, because that's usually what people are going to explain to you. But what you can do also is you can play the game of domains, right? That's one of the concepts that I didn't put in the slide further, but the concept of a domain is just an area where I transport something between two things. And that's why we call it multi-site. Right? I'm having 2 sites where here's like pod A and pod B, and I want them to intercommunicate between them. So you can see here that I can start playing the game of, oh, I will have multiple domains, so I can create a super nice hierarchy and connect everything that I want. But why do you want to do that? So let's take an example for the pod A, right? It's a very typical spine leaf. It's very tiny, 2 spine, 4 leaf. You want to grow that data center. How will you do this? Well, usually the easy answer is like, okay, I'm just going to add more leaf, right? I'm going to grow my DC, add more leaf, add more spine, it's going to work. That's one way, it works very well, right? The other way you can do that is you take your spine, you say, okay, these will be my border gateways where I do my tunnel termination, right? I can then take the same architecture, create a pod B, which is the green one, okay? And pod B is like a replica of pod A, and I just hook them up with that domain at the top, and I grow my DC this way. So I still have a data center, but instead of being just orange, now it's an orange-green. Why you want to do that? Well, actually, first of all, your blast radius is very limited to your color that I put in the slide. If you're working on the orange one, your blast radius is just orange. You can summarize at the border gateway, then you have your transport via that multi-site domain A, and you can continue to the green part on the other side. So therefore, you can put policy under your border gateway. You have much better control as well. But not only that, is if the pod A has been designed with whatever technology, right? My B side, maybe we cannot talk to that guy because it's a private protocols, whatever. But you can still extend that data center with the new gears by doing this trick. And from an external point of view, where I put the super spine, I will have also border gateways there. And anybody outside that wants to talk to my DC doesn't care. He's just going to talk to my 2 super spine / border gateway. And within that, I have a data center, which is 2 pods, 2 technology, but 1 DC. So you get the idea. So therefore, with what I find pretty cool is like kind of playing just a Lego game that I'm connecting stuff, and things will be well defined by those domains. And then I put here a ghost pod because I can also even grow it in the future. And guess what? Maybe you're gonna try a different OS on that one to grow it. You can use, I'm on part of the SONiC team, you can use SONiC on this. You can grow with your SONiC, with a SONiC component there, and say, well, but SONiC doesn't really talk with the other gears, it's an old gear. I don't care. With this, I don't care anymore. Because my domain is giving me all the flexibility to interconnect everything. So now, once I have my data center, right, and I have those border gateway nodes on, as the super spine indicated here, then I can connect it through the WAN to somebody else. Well, it is just another domain. So if you compare the domain A and domain B, they work the same way. From a protocol point of view, same thing. So now, this is where this whole architecture is making sense, because now you can do full extension of L2 and L3 via those domains, because it's just a transport. You can massively scale now your data center because your blast radius is limited to those corridors I was showing. So therefore, like, remember the pod A, it's a 2-spine, 4-leaf. Well, you don't get more than that. So from a scalability point of view, it's very, very limited. And then I have my B as well. Then you interconnect that. My data center is big because it's not 4 nodes, it's 8 nodes. But it's really, really nice from scalability point of view. It gives also clear ownership to each part. Sometimes also people get data centers and say, oh, I had that DC, and then suddenly for whatever reason, with my company, they get merged. And it's difficult to, well, now you can merge them. Multi-site FLNG is very good at this. So the concept. So remember, we talked already about one concept that you won't see hit, but is the domain. The domain is just like, how am I connecting data centers together? Now, the other things that you need to know is, and I'm going to start using DC and WAN because it's easier to explain than just domain A and domain B, because it's kind of difficult even for me to follow what I'm going to say. So for this, on the DC side, the concept, as I was saying, is that the tunnels get terminated at the border gateway. So therefore, if you're using VXLAN, you have a VTEP endpoint of your tunnel facing the DC side, and you will have completely a different VTEP facing the WAN side. Some people say, oh, you can use one. Yes, you can use one, obviously. But if you really want to decouple each section or each domain, separate them out. And the beauty is then you can start doing stuff like V4 or V6 anywhere where you want. So you can have a data center which is speaking V6, connecting to a V4 one, connected to another V6 DC or V4 DC, who cares? It becomes very, very, very simple. And on top of that is for debuggability purpose, you know exactly when the packet is flying, who is what. Because you're not mangling all your VTEPs into a single pool, right? So the second concept also is the border gateways are coming usually in pair for redundancy, right? And what we are defining here on top of the VTEP, because you will see on the picture that we have the PIP is the physical IP, VTEP facing the WAN, then you have the one facing the DC, as I said. But for supporting all the pairing, right, you want maybe to synchronize some protocols, your ARP cache, your ND cache, depending what you're doing. There's the concept of IESI. IESI is for Interconnect ESI. So remember in EVPN the concept of an Ethernet segment. It's a logical representation of a connectivity to your network. So here you're kind of in the middle, right? Because you're on the border gateway. I have a WAN on one side, I have the DC on the other side. What is an IESI? Usually you can do it with one, but you can have two IESI. One Ethernet segment identifier for your DC, one for the WAN, and then you're going to say, why are you doing that? If you have L2 traffic, you need to deal with BOM, right? And you're flooding, and your loops, and everything that can cause a duplicate packet, you don't want to deal with that. So therefore, you need to do your DF election about who is the DF, the designated forwarder, who is the non-DF. The ISIs serve that purpose for traffic coming from the WAN or from the DC. Now you're going to say, but why two ISI? We will see it later, but is it this failure? Let's say your border gateway is isolated from the DC or isolated from the WAN, but not from the other side. So how do you deal with that? How do you know? ISI is how, with BGP, you tell your peering border gateway, hey, I failed on the DC, take over, please. That's where all of this things will happen and make sense for you guys. So, now if you look at the border gateway itself, what did we do special? Nothing. It's nothing. It's usual construct that we do in the every life of EVPN and VXLAN and all of that, right? You have a bridge domain. We are connecting an L2 VNI for your L2 service on the DC side to the WAN side. And then I have a VERF for my IP traffic connecting my DC to the WAN side. And I put an SVI/IRB for doing my L3 gateway between L2 and L3 in betweens. In case I'm having a straight, connected host directly attached to the border gateway. And I can go to L3, I can go to L2, I can do all possibilities. So what is tricky here, right? In SONiC, it was tricky, because stuff like with the version in community, we did not support two different VNI for the VERF. That does not exist, so we needed to extend that. Same thing for the L2. We did not support two L2 VNI. So therefore, sometimes you get some constraint based on NOS, based on capability of your ASIC. So, but at the end, a border gateway is just doing exactly what everybody is doing it, like for other type of service, but you're just connecting them. And again, what was very important that I say at the beginning of this presentation is that a tunnel coming to your border gateway gets terminated, you do your lookup, and then you re-encap it, and you go. Now, the other concept that we need to talk about is the concept of a normalized VNI. Again, this is for VXLAN, which is... So the normalized VNI is what? Remember that domain, right? That's what we've been talking. We have the DC, we have the domain. The domain can be your WAN, can be just a stretch to another part of your data center. So what value are you going to use there? Well, first of all, the cool things that I mentioned to you is within that domain, I'm going to have my own VTEP, which can be V4, V6, which is cool. But then whenever I have my L2 service coming from the DC and I need to transit via that, let's say, WAN, well, what VNI am I going to use? And this is where the concept of normalized VNI helps. You just make sure that during that transport zone, you have a unique VNI for that service. So therefore, whenever you land on the other side of that data center, whenever you land on the other side of the WAN, in the remote data center, well, it's going to know that, oh, this is a normalized VNI coming at me. I will do my full termination. I'm going to map to yet another value within my DC. So now, instead of having this kind of mongrel of thing like you can see on the left side of the picture where you say, oh, I have like VNI 20, when I need to, I can go there and can go there. I mean, from an implementation and scalability point of view, it's super difficult, right? Even try to debug me, right? You're gonna have fun. But if you know exactly that your VNI 20, whenever it's end up, is converted to 1,000, and I can talk to another data center, which is his VNI is 40, because the 1,000, when it gets into DC2, it just gets remapped to that VNI value. It's fantastic. It's just purely logical. And it's super easy to debug. I mean, there's no question about it. But the other way that also you can do that, if you don't want to do normalized VNI, is using the downstream assigned VNI the way we do usually EVPN with VXLAN. The problem with that, well, first of all, there's good things about it, right? The good things about this is that for some implementation, as I said, that are very limited in terms of what they can do. They cannot have two VNI for the same verb, or two VNI for the same bridge domain. This is a very nice thing. Because now you can just, as a remote guy, tell me what value you need from me so I can connect with you. That is the concept of this, right? You tell me, oh, you want 40, I'm going to send you with 40. Oh, you want 23, I'm going to send you with 23. But then, from a scalability and resource point of view, you're going to burn a lot of them because they're all different. If I was going to a normalized VNI, I just need one value. I know that each time I go into that domain, is 1,000 I'm using. Not your value, not your value, not your value. Okay? So, but at the same time, if the guy is not capable to support two different value for the verb of the BD, well, you don't have a choice. So the other thing is also that some people were debating internally, because we love to debate at Cisco. It was about like, oh, but this is kind of cool because from an end-to-end design point of view of your network, I don't need to terminate all my tunnels. Some of the parts can just be a transit part. Because if I'm coming on one side and I know on the other side I have the same VNI value, and I will cheat it by using one VTEP, I can just transit. True? I don't disagree with that. I don't like it, but I cannot disagree with that. All right. So now, basically, that's the choice you have, right? As I said, if you want to have a common part to discuss, go and use the normalized VNI part, right? So basically, everyone agree about a unique value. So whenever you transit, you just reuse this and you go. Or ask your partner and say, tell me what value you need, and I'll do it. More complex, in my opinion, tougher to debug, and is using more hardware resource to apply that. The other things also, which is kind of cool, is the whole mobility, right, that we are always providing with EVPN, especially in data center. So with the concept of having that domain, that normalized places, right? But doing mobility is just as before. So for everybody who did play with mobility in data center, nothing has changed. Because remember, the domain that will stitch the data center part or pods, it's just an EVPN route, and the EVPN route will be carried over. So if your host is moving within a DC, nobody cares because your next hub hasn't changed from the outside world. But if your host is moving bit across DCs, well, EVPN will just re-update his /32 and say, oh, your next hub is no longer here, but it's there. So it's seamless. So there's no work. It just works as is. So let's look now a bit at the flow. All right, let's look at the L2 flow, okay? So this picture is very simple. You have a data center, you're going through a WAN, and you're landing into a different data center, okay? So you have your IP packet, IPv4 can be IPv6, but let's use it, doesn't matter. But what is important here is, how do we do the encapsulation with VXLAN? And it's very, very simple because your source IP is yourself, where you're starting, the beginning of the tunnel, and your dest IP is the end of the tunnel. So I'm starting at the leaf 1, so my source IP is leaf 1, I'm going to border gateway 1, so the destination is border gateway 1. I do full tunnel termination, then I need to jump on my normalized VNI tunnel. What do I do? Well, my source IP is now my border gateway as a source IP, and my destination IP is the other border gateway, the remote one, which is 3 in this case. Whoop, you go across, you land, tunnel termination, look up, rebuild. Source IP is my border gateway, destination is the leaf. So it's very, very, very simple. Nothing else. So at any point of time, if you do a PCAP on your packet and look at it, you know exactly where it came from, where it's going, and the content of it. And if you know the normalized VNI, you know exactly what you're stitching. And why is it transiting through that domain. If you look at the BOM, conceptually speaking, is the same. But remember, we discussed about the ISI, the Interconnect Ethernet segment. So basically, the 2 border gateways, one will be DF, one will be non-DF. So as a leaf, we will perform ingress replication of your packet, send copy to both. One of them will drop it, the other one will forward it, and then you reach. But in terms of encapsulation packet flow, it's the same as what we just discussed before. Because from an L2, the payload doesn't really matter. What matters is really how the tunnels are, the header of the tunnels, and what value we are using for the source and dest IP. Another way that people are doing this, by the way, and I've seen it, is if you don't have any locally connected host at the border gateway, right? So meaning that the border gateways are pure spine, right, or super spine. And you're just transiting to go somewhere, right? You still do the termination, but technically speaking, you want just to go somewhere, right? Nothing is getting originated or source originated from there, okay? People are using an Anycast VTEP, which is kind of cool because if you have Anycast VTEP, and I did this and I implemented it, and it works very well like a charm, is whenever the leaf is sending the packet, first of all, instead of sending 2 copies, we'll send only 1 because it's Anycast. And you're going to hit one of the 2 border gateway. The beauty is whenever you hit that border gateway, you just keep forwarding to the remote border gateway. So you don't need to deal with flooding and looping and all of that. Because by the virtue of being in Anycast destination, you cannot get it wrong. So that simplifies quite a lot your design. So Anycast VTEP in this type of scenario for L2, it's amazingly good. I really like it. And it makes our life very simple. But as soon as you want to support locally connected hosts on your border gateway, it's completely a different story. For L3, the packet flow is slightly different, right? Yes, we talked about this source IP and this IP, like for your tunnel header, is the same, okay? But remember something, which is kind of, I hate it, that's what it is. VXLAN, whenever you're terminating a tunnel, you always land the packet into a bridge domain. IP or not, by the way, guys, okay? So therefore, because that's how the pipeline of VXLAN has been designed in multiple years ago, I don't have the date, you need to make sure that the destination MAC that you're going is the right one, which is the router IP MAC of where you're going. So therefore, whenever you receive a packet, the first thing you're going to check is the destination IP of your tunnel header, and you're going to say, is it a for us? Check. Yes, it's for me. Perfect. Where do I go? You look at the VNI value, right? The VNI value will give you a bridge domain. You're going to say, but Patrice is L3. Well, it's a dummy bridge. Who cares? Just purely forwarding construct. Then you do a MAC lookup. Well, that MAC lookup is the router MAC. That will give you a dummy SVI. And the dummy SVI give you to the VRF. You say, oh, finally the VRF, yes. Then you do your IP lookup and you keep going. So this is why you're seeing here in that picture that the source and destination MAC are always changing. This is a nightmare, but that's what it is. However, I truly believe that if we start doing or implementing an L3 VNI as an interface, we can skip all that crap. So from the L3, from the VNI value, you can land directly into the VRF where your IP lookup will happen. And I think that's the best design, because you don't need to go through that hop of dummy BD and dummy SVI and if this blah, 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 blah. Just keep it out. Like MPLS doesn't need that. I mean. All right, isolation failure. Okay. So the beauty about this whole design also is it can survive quite drastically a lot of failure types, especially around your border gateway node, okay? So let's say in this example that the border gateway 2 is completely isolated from the WAN, from that domain. And in this picture, obviously, I added a locally connected host just to prove the concept. Okay, so it is H2 connected directly to border gateway 2. You're gonna say, why you do that? Actually, yeah, let's take a side note on this. Whenever you're building very cheap data center, right? Usually you have spine leaf. And one of your leaf is gonna be a border leaf, where you wanna go somewhere, right? You can have like, maybe running VRF light, going to a northbound customer with IPv4, IPv6 plain GRT, right? You can do that. You're allowed to do that. Or you can just have one connected host there as well on that one. But then whenever you're building those cheap data centers, some people will say, but Patrice, you're asking me also to pay the price for having a border gateway. Why do I need to have both? True. So this is why most of the people, well, not most, some of the people, what they're going to do is take the border leaf functionality of going VRF light or to northbound customer or having more connected hosts and bring that up into the border gateway nodes. So they take those two boxes and make it one. Okay? So if you make it one, then you can have the scenario exactly like this, where you have a host 2 which is hanging up the border gateway. That's the concept behind why people do that. So to save money because they have less hardware to buy, basically. At the end, that's what it is. All right. Now, since we are disconnected from the WAN on border gateway 2, how do we get the communication from border gateway 1 to border gateway 2? Well, you're going to say, well, it's easy. You're going to go through the DC. Okay. That's one way of seeing it. But how? Because earlier I was explaining my DC can be V6, and my WAN can be V4. So how can I transit through the V6? They won't know where this is, where that destination VTEP is, because I did it on purpose to separate them out completely, so it's easier to debug and all of that. So how do you do that? So the first thing you can do, which is very easy, you take your V4 address from the WAN, you leak them into your DC. And you take your V6 address from the DC, you leak them into the WAN. But you get people who say, you're running nuts? Because then you need to support dual stack. Yeah? But that's one way to do it. Because otherwise, your underlay won't know where to forward your packet, right? If they don't see each other's. The other way to do that is to add an interconnect and link in between the two border gateway, which is only for an L3 underlay purpose. You can set up two sub-interfaces on it, and each of them run different BGP peering session, one V4 for the WAN, one V6 for the DC. They will exchange and everybody will see each other's. Okay, some people say, yeah, but you have an extra cost of the link. Yeah, okay. I can live with that. Personally, some people cannot, but I can live. Or you can do the leaking. Or if you just support V4 everywhere, well, leak them out, and you don't have dual stack, it's just V4 and V6, same thing. So those are pretty much the choices that you have. But now the beauty is that if somebody on the WAN side wants to talk to H2, he has the destination VTEPs of the border gateway 2. So therefore the packet, right, because now the underlay knows how to reach it, will go to the border gateway 1, but instead of terminating the tunnel there, because whenever the border gateway 1 receives the packet, they say it's a for us check. It's going to look at the packet and say, oh, is it for me? No. Ha. So the tunnel is not getting terminated. You just do an IP transit. You ship it to the border gateway 2, where the termination will happen. And then you can talk to the host 2. So it's kind of simple, but that's what this is. So basically, you're in this exact scenario, border gateway 1 play a role of a kind of just pure spine or P functionality from the packet point of view. So H2 can talk to anybody in the WAN now. From a DC point of view, whenever you have an isolation, you know what is the beauty about this one? Is everything I just explained is the same. It works exactly the same, right? Because your reachability happens in the underlay. So therefore, I mean, who cares? It's exactly the same. So basically, whenever you're building your logic and your node doing this, it doesn't matter. And if you have like a full border gateway, failure, the node is completely gone, well then and everything we discussed really doesn't matter neither, because it's not like that. You have just another border gateway taking care of all the traffic. And the guy who is connected to border gateway 2, he's gone as well anyway. Okay? So with the multi-site technology, with using the interconnect for providing it, you can see that you can support pretty much any type of configuration, any type of connectivity, and any type of failures behave the same way. And you can it's really nice because you can make it like per domains with your own policy, and then you don't need to, and from a debuggability point of view, each time you do a PCAP or you want to look at the packet, you know exactly what is going on, what is happening. So I put this wonderful table just for fun, just to prove that it works. So if you do that table, where the P are the permits, so you allow what is happening, and the D is the denial, and you put that in your stuff, in your implementation, it works. So you can try it, or you can trust me, but I was kind of finding funny that I was putting there because nobody wanted to understand that table, so anyway. So the way it works is very simple. So the left column is where the packet is coming from. Right, if I'm coming from data center unicast, where am I going next? That's each of the column. And then you look and you say, am I allowed or not allowed? That's how the table works, okay? So if someone finds a bug, please send me an email. I will be very happy because that's what I implemented, so hopefully it works. All right, so okay, to summarize, what did we discuss? As I said, because you can confine some part of your network with that and limit your blast radius, it's very good for scalability. See, if I have 2 spines for leaf, the number of routes I'm going to learn, my ingress replication, the policies I need to support is limited to that. If I put it like huge data center of 128 nodes, and I have like different level of we have spine, super spine, then my blast radius is much bigger, more route. So we need bigger hardware, better hardware, right? It's all of that. So confining it and downsizing what you're doing and use border gateway helps for that, especially if you want to buy very cheap gears. Now, everything about EVPN and the mobility comes for free. You don't need to do anything. It just works. There's no, you won't see any new RFC, nothing. The concept that exists today works. All the construct that we talked about, the BD, the VERV, the SVI, it's the same. Nothing has changed, right? We cover the full resiliency as well, right? For the failure, I explained to you the trick. You either put a wire in between, or you just leaked the addresses, or put it in flat. All of that works very well. And then also you can enforce any policy at the border gateway because you can do summarization, you can put route maps, you can do whatever there as well. So those are all the cool things that I like about it. So there's been a lot of work in the past. And I know some people say, hey, these drafts are not active. I had that come. Yes, but I did want to put it there to show you how much work people put there and put their thought. Yes, the RFC is out. 9014 is the way to go. But there was also the draft that people has tried, and this whole things came together because of this work as well. So it's just not like one thing that happens now. It was like through effort via multiple things, but it came out with one RFC. So that's it for me today. Any questions?